Hello students, welcome back. Let's resume our discussion in section 2. We went through the greatest common divisor like this. Given a pair of integers R and S, we can form a set like this, the set of all linear combination, and R plus MS form, where M and N are integers. Then you can prove that this is a subgroup. So it's a subgroup of a cyclic group, so it's cyclic and it must have a generator. If one is generator, then negative of that is also a generator, so one of them has to be non-negative. So we take non-negative generator, and that's what we are going to define as the GCD, but not so fast. The non-negative D generating this set H exists as, but how many? Not just yet. So let's go ahead a couple more. It's a common divisor, and also it's the greatest common divisor. Okay, especially the second thing. Finally, we have the uniqueness. So we can define D as the greatest common divisor, the non-negative generator of this. So we have to have this linear combination expression. We have to have this common divisor. We have to have the greatestness, and so on. Okay, what about the next example here? Euclid lemma? Okay, alright. If two integers R and S, if two integers R and S are said to be relative prime if GCD is 1. Okay. This result is known as the Euclid lemma. If R and S are relatively prime, that is GCD is 1, and R divides S times M, then R divides M. If you have prime factorization idea, then this is really easy to understand. GCD of R and S is 1, so R and S do not share any prime factor. So all the prime factor must be in M, so R divides M. That's the idea, but there's a problem. As for the prime factor and those kind of things, we didn't prove any of those, and actually that's difficult to prove. And also, if we go beyond number theory and establish something similar with, say, polynomials or things like those, then what do you mean by prime? Those kind of things has to be re-established. So prime factorization is something we want to avoid. Instead, we're going to use this GCD. That is NR plus MS is 1 for some N and R. So GCD is, so N0R plus M0S is equal to 1. That's what we are going to do. So you see, remember, D is a non-negative generator of sets of this form, NR plus MS form. Okay, this form. So D belong to this set. So a certain integer N and M exist so that D is NR plus MS. Those integers are named as N0 and M0 respectively. So using that, can we prove this? Excuse me. Oh, I didn't do this right. I gave you an illusion this M and that M are related or similar. Oh, I shouldn't have done that. Let's rewrite like this. Okay, so is set of A, R plus B, S, and A and B belong to set of integers. Okay, let's write like this. D is a non-negative generator of the set. We used to use H here. And this is a subgroup. We proved it. And then it's a subgroup of a cyclic group Z. So it has a generator. And among them, we're going to select non-zero generator. So that's how you do it. And then D must belong to this. So A0, R plus B0, S. And then this happens to be 1 in this particular case. Let's not use M and N because M is already used up here. Okay. Okay. And then from here, let's work this out. From here, multiply M to both left-hand side and right-hand side. A0 RM plus B0 SM equals to M. That's what I get. Okay. And then, please note that this SM is divisible by R. So this whole thing can be rewritten as SM is something times R. Say T times, T times R. I'm making this highlighting so that you can see. That's how things were replaced. So from here, multiply M to both left-hand side and right-hand side. And then R divided SM. So SM is something times R. Let's say T times R. Now, do you see the conclusion? R divides M. R belongs to here and also there. So if I factor R out, then I get A0 M plus B0 T therefore R divides M. That's a computation and that's a proof. What did I do here? Yep, I just gave you a sketch, some idea, not the full proof here. Okay, that was Euclid lemma, and here's another example. What about the least common multiple? Given pair of integers R and S, prove that the set of all common multiples R and S forms a cyclic subgroup of Z under the addition. Here, the positive generator of this cyclic subgroup is called the least common multiple. I think you should have called non-negative generator. For a special case, R and S are both 0. In that case, you're going to get 0. But let's forgive the textbook author. Or maybe there was the additional condition, R and S are not simultaneously 0, which I missed. Anyway, so set of all common multiples. So N is a multiple of R, and S is multiple of N is multiple of S. That is, S is a factor of N, and R is a factor of N. And set of all such N's forms a group. In other words, you have to check the three things. Close under the addition, and then 0 belongs there, the additive identity, and the inverse belongs there. Well, the second thing is easiest. 0, yeah, everything divides 0, so 0 belongs there. And then if N belongs there, negative N also belongs there, you see. Something divides N, then it automatically divides negative n as well. Just multiply the negative of the quotient. So close under the addition, that's something you have to sweat on. Okay. Next, given R1, R2, R3 all the way over to Rk, all of which are integers, prove that the set of all common multiples of R1 to Rk form a cyclic group of C under the addition. That is, set of all n where n is a multiple of all Ri, and you can prove that this is a subgroup of Z. So it's a cyclic subgroup, so it must have the generator L, and that's what we call the least common multiple, LCM. Again, you have to prove those three things, and the first one will be the hardest. Closed under the addition. How do I do that? As for the 0, no problem there. Everything divides 0, so 0 certainly belongs there. And then, how about the inverse? If n is there, then all those Ri's divide negative n as well. So, replace the quotient Qi by negative Qi. See? N is Q or I. Then all you have to do is this. So if Ri divides n, if and only if Ri divides negative n, you see. So second and third are easy. Close under addition. Well, that's going to be a bit of a work. Good luck. If you can do this, you can extend that idea to more numbers to get that. May look pretty straight ahead. Maybe you need induction. I don't know. I haven't thought about it deeply yet. Anyway, those are left as homeworks. Okay, so much for section 2. Let's meet again with section 3 in a separate video.